We move on to stresses in rigid pavement. You have to take note that there are stresses that is developed in rigid pavement. So what are what are the causes of the stresses? So it may include the action of traffic wheel load, the expansion and contraction of the concrete due to temperature changes, the yielding of the subbase or subgrade supporting the concrete pavement, and volumetric changes. So basically that is that is caused by the stresses that is developed on rigid pavement. Traffic wheel load will induce flexural stresses that are dependent on the location of the vehicle wheel relative to the edge of the pavement, whereas expansion and contraction may induce tensile and compressive stresses which are dependent on the range of temperature changes in the concrete pavement. So basically, this is now the illustration showing to us the deformation on a beam on elastic foundation. This is due to bending. So the ability of the rigid pavement to sustain a beam-like action across irregularities in the underlying material suggests that the theory of bending is fundamental to the analysis of stresses in such pavement. So for this one, if the stress induced by bending that is being developed on the rigid pavement, so we have to adapt the fundamental of the theory of bending that may occur on our rigid pavement. So the stresses that is being developed in the beam can be analyzed by assuming that the reactive pressure, which is proportional to the deflection, is developed as a result of the applied load. So this pressure is actually given by this equation. Reactive pressure at any point beneath the beam is equal to modulus of subgrade reaction multiplied to deflection at the point. So for this one, we have here a general relationship between the moment and the radius of curvature of a beam, which is given by this equation. 1 over radius of curvature is equal to moment in beam all over modulus of elasticity times moment of inertia. Then we move on to stresses due to traffic wheel load. So actually the basic equation for determining flexural stresses in concrete pavement due to traffic load was first developed by Westergaard. Actually, Westergaard considered 3 critical locations of the wheel load on the concrete pavement. So we have here the first case, which is case A, load is applied at the corner of the rectangular slab. The second case B, load is applied at the interior of the slab at a considerable distance from its edges. And case C, load is applied at the edge of the slab at a considerable distance away from the corner. So this one is an illustration showing to us the critical location of wheel load on concrete pavement. So if we can observe here, this is the position for our load, which is applied at the corner of the rectangular slab. So this is case A. Then we have our case B, wherein the load is applied at the interior of the slab at a considerable distance from its edges. So this is case B. So this is the load. Then case C, this is case C, wherein the load is applied at the edge of the slab at a considerable distance from any corner. So this is the edge of the slab. So this is the position for our case C. Then we have stresses due to temperature effect. So the tendency of the slab edges to curl down during the day. So the slab edges curl down during the day and it will curled upward during the night because of the temperature gradient, which is resisted by the weight of the slab itself. You have to take note that the resistance tends to keep the slab in its original position, resulting in stresses being induced in the pavement. And compressive and tensile stresses therefore are induced at the top and bottom of the slab respectively during the day, whereas tensile stresses are induced at the top and compressive stresses at the bottom during the night. So we have here the formula for the maximum curling stress at the edge of the slab in the direction of the slab length due to the temperature difference between the top and the bottom of the slab. This one is the formula for the maximum curling stress at the interior of the slab in the direction of the slab length due to the temperature difference between the top and bottom of the slab. So the difference here is the location. This one is for the at the edge. This one is at the interior of the slab. Then we have a formula for the frictional force, capital letter F, that is developed due to a uniform drop in temperature. For the thickness design of rigid pavement, so we have to, the main objective actually for a rigid pavement design is to determine the thickness of the concrete slab that will adequate to carry the projected traffic load for the design period. So for this one, for the thickness design of rigid pavement, we make use of the AASH2 method, wherein we have to consider some design considerations. So that includes so for this one, for the AASH2 design method, we consider in the design the pavement performance, the subgrade strength, the sub-base strength. We have our traffic, the drainage, reliability. So those are considerations for the design of the thickness of the rigid pavement. So using the AASH2 method. Now we also have the Pca Design Method. The Pca method for concrete pavement design is based on a combination of theoretical studies, which results of a model, and a full-scale test, and the experience gained from the performance of concrete pavement, normally constructed and carrying normal traffic load. So for the design consideration for Pca Design Method, we have to consider the flexural strength of the concrete, which is used in the procedure as given in the terms of rupture obtained in the third point method as indicated in the ASTM designation C78. And we have also considered the subgrade and sub-base support. So for this one, the Westergaard modulus of subgrade reaction, small letter k, is used to define the subgrade and sub-base support. So actually, this can be determined by performing a plate bearing test or by correlating with other test result. Then we have to also consider the traffic load, which is computed in terms of cumulated number of single and tandem axles of different loads projected for the design period of the pavement. So those are considerations for the design for our rigid pavement using the Pca method. Now we also have Mechanistic Empirical Design Guide method. So actually this design procedure is presented for the jointed plain concrete pavement, or the JPCP. As the design of the continuous reinforced concrete pavement, the CRCP is beyond the scope. Actually, for this design process also involves three major steps. So it involves the determination of the input values of the trial design. Step 2 involves the analysis of the structural capability of the trial pavement through the prediction of the selected performance. And the last stage is the evaluation of the structural viability of the trial design. So basically for this MEPDG method, we have three stages. So it involves, basically we have the trial design. Then after you identify the values for the trial design, you're going to identify the structural capability of the trial design, or the trial design is considered the trial pavement. Then the last stage is to evaluate the structural viability of the trial pavement or the trial design. So the traffic, foundation and subgrade soil and material characteristic for which input values are required are similar to those for the flexible pavement.